geometries and bonding theories, and this is going to start to go over all of our heads by the end of this chapter. Not the geometry part. The geometry part you guys will be fine with. That's no problem at all. It's some of the bonding theories. We're going to talk about a new bonding theory called molecular orbital theory, which is actually probably quite a bit more correct than the Lewis structures and the valence shell electron pair repulsion that you learned last year. But it's also a lot more difficult. So we're not going to, the good news is we're not going to get into too much depth about it, but it will kind of make your brain hurt a little bit. But there's the introduction to Chapter 9. So molecular shapes, that's easy, okay? You guys did this last year. That's no problem. I will try to get you a sheet like you had last year with these molecular shapes on them. The bad news is you don't get that sheet for the AP exam, so you actually have to memorize it this year. But the good news is, well, I really wanted to give you some good news there, but I don't have any. Sorry. Yeah, for a while you'll have a sheet to look off of until it matters and you're actually taking a quiz or a test.
I feel like if you use it enough,
what? I'm sorry. Yeah.
But I feel like if you use it enough, you'll accidentally memorize it.
Yeah, that's okay. So maybe that's the good news, is that it's not that hard to accidentally memorize. Yeah, I am kind of just making that up now, but you know, it's something, right? The good news is you guys are smart enough to memorize things. There you go. Okay. Good news is you're breathing right now. You're still alive. Your heart is beating. Yeah. Sorry. Okay. So anyway, so molecular shapes. I'm looking for a good picture here of all the shapes, and then I'll come back to some of this stuff. It's valence shell electron pair repulsion is the whole idea here. Was that it? I want like one that has all of them, but I'm not sure if I have one like that. This is the worst possible way to be scrolling through this right now.
You can just like close it and then like, yeah.
Let's see.
There you go.
Is this it? Maybe? No? I thought I had one that, oops, I just think I moved something. I thought I had one that had everything on it. No, I guess they're all individual. So I'll point you to the pages in the book, I guess. Page 350 has a good summary. Well, actually, I guess between page 347 and page 350, that's probably the worksheet that I'll give you, is just a copy of 347 and 350, because that basically walks you through all of the different geometries. And this does too. It just does it a lot more step by step, so you have to kind of talk about each individual one. But the main idea that you got to remember here from last year is the electron domain idea. You guys remember that? So you count the number of domains around the central atom. Okay. Now remember things like double bonds. Whoops. Or we could talk about glucose.
I like glucose.
Things like double bonds, they only count as one domain because those electrons have to stay together, right? So basically what this is, it's just the electrons are trying to get as far away from each other as they possibly can. So we think about the geometries they can actually use to do that, right? So, and the trick here is, once you get past 3 electron domains, you have to start thinking in 3 dimensions instead of just 2-dimensionally, okay? For the first 3 pairs of electrons around the central atom, it's not that difficult. And actually, you really only have to worry about when there's 2 domains around the central atom. You don't have to worry about 1 domain around the central atom. That's just a bond, and it's going to be linear, right? And there is no central atom if there's only 1 domain, because there's just 2 things like, you know, HBr, right? Although I guess that, yeah, bad example. Anyway, moving on. Point is, you count the number of domains around the central atom, okay? And this one, for example, A has 4 here, okay? So because it has 4 electron domains, do you guys remember by any chance what kind of geometry that's going to be? tetrahedral. Yep.
I have that packet. I know I have it.
Yeah, so
It's in that folder, but I left it at home.
so this would be maybe a good one to look back on your last year's notes. There's not a lot that's new here as far as the shapes are concerned. So, yeah, basically you're just counting electron domains. You're looking at those shapes to see what they're going to be. And they will typically focus on the easier to remember ones. Although I have, on an AP exam, I have seen them throw in a T-shape every once in a while, or a seesaw, you know. But those tend to be on older AP exams. I think the trend as they get into the more recent years is that they're sticking with the ones that are a little bit easier so that there's not as much memorization you have to do. But I'm going to make you know all of them because you never know what they're going to throw at you on the AP exam, and I want you to be prepared. So anyway, if you look at page 347, you've got your linear molecules. If you have 2 bonding domains and 0 non-bonding, then the way that those 2 domains get as far away from each other as possible is just to get on opposite sides of the atom, of the central atom. Okay? So once they do that, then they're going to form a linear bond with anything else they bond with. Okay? Trigonal planar, again, we can still think in 2 dimensions here. You've got 3 bonding domains. And those 3 domains, to get as far away from each other as possible, they just need to be at 120 degree angles. Okay? If you have 2 bonding domains, and one of those is a lone pair, or a non-bonding domain, then it's going to look like a bent structure. Okay? And again, they have a picture of that there. You've just got the lone pair up at the top, but the actual, the molecule is going to look bent. Okay? You're not going to be able to see that lone electron pair up at the top, but it will be, you'll be able to see its influence. Okay? The tetrahedral, you've got 4 bonding domains and 0 non-bonding. That's going to be the typical tetrahedral shape. If you've got 1 lone pair, you take the atom off the top and make that a lone pair instead. Then you've got basically a pyramid type structure, so it's called trigonal pyramidal. If you take 2 of the atoms off and now you have 2 lone pairs, then you have something that's really bent. Okay? I don't know why they call that. They should call that really bent, as opposed to, you know, when you have 2 bonding domains and 1 non-bonding. That's just a little bent, right? But they don't do that. Probably better they don't consult me on these things. Trigonal bipyramidal on page 350. You've got 5 bonding domains and 0 non-bonding. So and this one's a little bit tricky, but the most stable configuration there is getting 2 of them at 180 degree angles from one another, and then the other 3 are in a plane at 120 degree angles. So the angle between the top atom and any of the atoms in the plane is actually 90 degrees. Okay? And here's where it gets a little weird. If you take a lone pair off, you're going to have to take it off in the plane. Do you remember talking about this last year when we had our gumdrops? Okay? Because the ones in the plane are 120 degrees away from each other, and those lone pairs of electrons, they don't like to be around other electrons. So the lone pair is going to be in the plane, okay? And so you end up with the seesaw shape. I don't know if you guys can see that or not. What's that? Yeah, you do sort of have to, especially with this. Now, it was easier when you had the gumdrops and you could actually build your little seesaw and watch it go back and forth. Yeah, we may have to do that again. But probably not. Yeah. We don't have time for fun stuff like that. Let's see, where am I here? That's tetrahedral. Okay, trigonal bipyramidal. So they actually distinguish between the axial and the equatorial. I don't think you're going to need to know that distinction, but equatorial just means it's on the equator, right? And axial, you're talking like North and South Pole type thing. So basically, the first 3 atoms that you take off to make, you know, if you take any atoms off and put lone pairs there instead, they need to come from the equatorial bonds, here, here, and here, before they come from top and bottom, okay? Because that allows them more room to spread out if they're in the plane. So eventually you could get to a place where you take off 3 of the atoms, you have 3 lone pairs or 3 non-bonding domains, and then it actually ends up being linear again because the only thing you have left is this right here. Okay? And then you got octahedral, that's 6 around the central atom. And again, I know there was some confusion last year. Why is it called octahedral if there's only 6 atoms around the central atom? Where is it? Here's octahedral. And basically what it is, you're not going to be able to see this very well on here because this is so small. Here, let me enlarge it for a second. Not that this will help that much. But if you draw from the top one down to each of the sides, like this, then you do the same thing. Whoops, I didn't do one to the, well, see, I can't, it's supposed to go over there. This is just not looking so nice. It's hard in 2 dimensions, and I think I missed one of them. Yeah, I didn't get this one. Or did I? I don't know. Anyway, point is, when you do that, you end up with something with 8 sides. Just trust me. Trust me on that. I didn't draw it very good. Basically, if you draw a line from this one to all of the atoms in the plane, and then you draw a line from this one to all the atoms in a plane, you end up with an 8-sided figure. So that's why it's called octahedral. Okay. All right. Anything else I need to talk about with the molecular geometries? Other than reminding you that we really don't know whether those expanded octets have anything to do with the orbitals anymore, and actually kind of suspect that they probably don't. There's not a lot that I need to talk about there. But what that leads into, it leads into the idea of the polarity of a molecule, all right? And that's really not that difficult, I don't think, but we talked about this last year. I guess I accidentally saved this on my video from last year. But bond dipoles, okay? So here's an example of a molecule that has polar bonds, and they'll ask this question sometimes on the AP exam. If a molecule has polar bonds, or which of these molecules has polar bonds but is a non-polar molecule, all right? So this has polar bonds, right? Because the oxygen is pulling harder on the electrons. It's more electronegative than the carbon is. But what you end up with is a cancellation of your dipoles, right? And you kind of have to think physics here for a second. It's kind of like vectors in physics. If you've got a vector pointing this way, and you've got a vector pointing this way, then they just cancel each other out, okay? So if you're pulling with equal forces on either side of something, then the object doesn't move, right? Not all of you have taken physics, I don't think, but if you know, it's like tug of war, right? So you're pulling, if both sides are exactly evenly matched, then the flag that's in the middle should never move, in theory, okay? That's kind of what's happening here, all right? The oxygens are pulling with equal strength both directions on the carbon, and so basically the dipoles cancel out and you end up with no overall polarity in that molecule. So the molecule doesn't have a charge. All right? If a molecule doesn't have a charge, that leads into the idea of intermolecular forces, which we're going to talk about later in the unit. So this actually is a very important concept that you need to make sure that you understand, the idea of polarity. Okay? Now, if you look at a molecule like this, now notice, if you were just drawing the Lewis structure for this thing and you thought, oh, okay, here's my Lewis structure, it looks like the dipoles would cancel out in that one, doesn't it? If I drew it that way, it looks like probably, I mean, they'd both be pointing towards the oxygen, right? And they would cancel each other out. But that's not what really happens because the actual shape of this molecule is more like this. So because of the lone pairs on the oxygen, it bends the hydrogens down. The oxygen pulls the electrons more closely to itself, so you end up with an overall negative charge on this side and an overall positive charge on this side of the molecule. So water is polar, okay? And that's why. Does that make sense? You remember talking about that last year? That's not making sense. What's confusing you about that?
I've never done anything with the thing.
Oh, okay. you don't have to use the soup ladles necessarily. That's just a way to say partial negative, partial positive. And in a covalent bond, we don't have an all-out, like one electron has been given to something, so it has a 1 minus charge, or an electron has been taken away from something, so it has a 1 plus. But the electrons are being pulled a little bit closer to one of the atoms, so we call that a partial negative, partial positive charge. It's not a 1 minus, less than a 1 minus, but it's still kind of a minus charge. Does that make sense? So that's what the soup ladles are really telling you. Not the hydrogens themselves, okay? Because remember, the nucleus of hydrogen doesn't really want to go that close to the nucleus of the oxygen molecule, right? But it's the electrons on the hydrogen that it's sharing with the oxygen, because really we've got, if I draw this like this, maybe it makes a little more sense. Those bonds, it really means there's electrons being shared in there, right? Okay, and then you have, obviously, your lone pairs up here. Why is it doing that to my dots? But these electrons really are quite a bit closer to the oxygen because the oxygen pulls them closer to itself, okay? So because these electrons are closer to the oxygen gets a little bit negative, and the hydrogens get a little bit positive, okay? And then if you take into account the shape of the molecule, it looks like this. So if the oxygen is pulling the electrons a little bit closer to itself, then this whole side of the molecule up here is going to be a little bit negative, and this whole side down here is going to be a little positive. Does that make sense? Okay. So then you end up, if you have something where one end of the molecule is negatively charged, the other end is positively charged, then we call that a polar molecule. Okay? And the implications of that are that when water gets close to another water molecule, if you get a positive end attracted to a negative end of a water molecule, water is actually attracted to itself because it has those charges, right? So you can, did I bend water for you guys last year? I don't remember if I did that or not. Did I? With the burette, you had the little stream coming out, and yeah. So you can actually bend water. If you have a charged glass rod, you can make the water bend towards or away from the rod, okay? Because water has a charge to it. That's also the reason that surface tension happens, right? Water is attracted to itself, so it sticks together on the surface, and so little bugs, if they're light enough, can walk across the top of it, okay? Or you can put a needle on top of it without it falling through, those sorts of things. It all has to do with the polarity of water, okay? What else here? So basically, and that's all the detail we go into on that right now. You just need to be able to look at a molecule, and essentially now you've got like 7 steps in this process, right? So I give you a compound, BF3. You draw the Lewis structure for it. It's probably not 7 steps. You draw the Lewis structure for it. You count the number of electron domains around the central atom after you draw the Lewis structure. Based on the number of electron domains around the central atom, you figure out the shape of the molecule, okay? You examine the electronegativities of everything, and you decide which direction the electrons are going, okay? You'll always draw your arrows towards the more electronegative element, right? So in BF3, for example, fluorine's the most electronegative element on the periodic table. So arrows always go towards fluorine, no matter what, okay? So the arrows are going towards the fluorines, but because this is a trigonal planar right here, that they all end up canceling each other out, and so we end up with a non-polar molecule at the end of all that. Okay? Remember the idea of symmetry. That's what helps you with polarity. You remember talking about that last year? If a molecule is symmetrical, then it's probably nonpolar. Okay? And you can usually tell if something's symmetrical or not based on whether it has lone pairs of electrons or not. You remember talking about that? There's a couple exceptions to that, okay? But for the most part, if something has lone pairs, it's going to be asymmetrical, which means it's going to be polar, okay? If it doesn't have lone pairs, and you have the same type of atom connected to everything. Now, an example here, see? CH3Cl. That's tetrahedral, but there are 3 hydrogens here and there's 1 chlorine. So that's asymmetrical, right? Because you've got a different atom up here than all the other atoms that are attached to the carbon. So that's still going to be polar. even though tetrahedral usually would be nonpolar. All right? So those are basically the kind of things you have to look out for here. I don't think you're going to have too much trouble with that. 9.4 to 9.6 gets a little bit trickier, but we talked about that last year. 9.7 and 9.8, we're just going to skim through very briefly, talk about molecular orbital theory, but we'll be through this chapter before you know it, and then we'll be talking about intermolecular forces again. So not a lot of new in this unit, which is kind of good news. It's a lot of stuff that we learned at the very end of last year, so it should be fairly fresh in your brain. Yep. All right. See you guys in class.